Masharu, చెప్పండి సార్. Right, start చేయండి Masharu. Go ahead, sir.
Good evening to all participants. On the occasion of 103rd birthday celebrations of Dr. Komaravolu Chandrasekharan, our department is conducting a 5-day international faculty development program on applications of mathematics in various fields with innovative approaches. Successfully, we have completed 2 days in our 5-day international faculty development program. On the first day, Dr. N. Sudhakar Garu, Professor, Department of Computer Science, Bapatla Engineering College, Bapatla, delivered a talk on machine learning models. On the second day, that is yesterday, Dr. K.N.V.V. Prasad Garu, Assistant Professor, Department of Mathematics, Guru Ghasidas Vishwavidyalaya, a Central University, Bilaspur, delivered a talk on the problem of discontinuity at a fixed point. For the above 2 sessions, each session is engaged with approximately more than 700 participants. Thank you one and all for your good response and valuable support. Now I request our head of the department and convener of this faculty development program, Dr. KVLN Acharya Garu, to address the participants.
Dear esteemed faculty members and distinguished guests, as we convene on this third day of our International Faculty Development Program, I am honored to take it as a pleasure to address the gathering of such dedicated and passionate participants. Our journey over the past 2 days has been a collective endeavor to enhance our skills and to expand our knowledge. I want to express my appreciation to each and every one of you for your sincere participation. It is through only your presence that we have transformed this event into a good platform for professional growth and collaboration. Throughout this FDP program, you will get an idea on innovative teaching methodologies and emerging trends in education. The wealth of experience in participating in any FDP definitely may combine with increasing enthusiasm to learn new things and exemplifying to explore the spirit of continuous improvement. Today, we have two eminent resources persons with us, Dr. N. Panikumar Garu from India, Dr. C.V. Pavan Kumar Garu from USA. I have a good association and valuable collaboration with both of them for many years. Both are down to earth and accomplished notable achievements in teaching as well as in the research field. 3 of us proudly say that we are the students of a stalwart and mathematical giant Dr. N.C.H. Pattabhiramacharya Garu, retired professor, NIT Warangal. We are inspired by our great guide, Professor N.C.H. Pattabhi sir, in all aspects, and he gave a new life for us in the field of research. In this memorable day, we humbly pay our heartfelt gratitude to him. On behalf of Maths Department, I am thankful to our today's resource persons to accept our invitation for giving their valuable lectures in our international FDP. In the third day's program, I am sure that the knowledge which will be shared by our revered resource persons, Dr. N. Panikumar sir and Dr. C.V. Pavan Kumar sir, which enable us to resonate in our teaching practices for reaching new heights. Thank you one and all. Let us continue to strive for excellence in education. Thank you. Thank you very much.
Thank you very much, sir, for your valuable message. Today is the third day in 5-day program, and today's speakers are Dr. N. Panikumar Garu, Professor and Head, Department of Mathematics, Vijnan Institute of Technology and Science, Hyderabad, and Dr. C.V. Pavan Kumar Garu, Faculty in Mathematics, Apex Max Excel Center, North Carolina, USA. Now I request one of our staff organizers, Ms. I. Rajeshwari, to present profound profile of Dr. N. Panikumar Garu.
Good evening all to a 5-day international faculty development program on applications of mathematics in various fields with innovative approaches. It is my privilege to introduce today's resource person, Dr. N. Panikumar Garu. Dr. N. Panikumar Garu is a senior professor working as a professor and heading the Department of Basic Science and Humanities, Vignan University of Technology and Science, Hyderabad. He did his MSc in Mathematics from Acharya Nagarjuna University, Guntur, MPhil from Sardar Patel University, Gujarat, and PhD from Acharya Nagarjuna University, Guntur, for the thesis entitled Some Mathematical Models of Ecological Commensalism under the guidance of Professor N.C.H. Pattabhiramacharyalu Garu, retired professor, NIT Warangal. He has published 32 research papers in various reputed international journals. Three students have obtained PhD under the guidance of Dr. Panikumar Garu. He is an editorial board member for one international research journal and associate editor for one international research journal. He completed TechUp 3 project of worth 2 lakhs rupees from Jawaharlal Technological University, Hyderabad. He delivered few invited lectures at NIT Warangal. Presently, Dr. Panikumar Garu, working in the areas of mathematical modeling, differential equations, modeling in epidemiology, ecology, and dynamical systems. Professor N. Panikumar sir has got good feedback and appreciation from all his students with his best way of teaching for the last 2 decades. His good attitude, friendly nature, teaching abilities, research capabilities are additional advantages to him apart from his experience in the field of education and research.
Thank you, Ms. Rajeshwari, for your nice introduction about Dr. N. Panikumar Garu. Now I hand over the session to Dr. N. Panikumar Garu. Dr. Pani sir, please start the session.
Okay, sir. Thank you. And before going to start my lecture, I'm very much thankful to the management, principal, and head of the department of Bapatla Engineering College, Bapatla. And I'm very much proud because I'm the alumni of Bapatla Engineering College, Department of Mathematics. And I'm thankful to my gurus, Dr. T. Srinivasarao Garu and Mr. Karunakar Garu. Thank you for giving this opportunity. And now I'm going to start my lecture. So now I'm going to share. Right. So all of you getting by this sharing PPTs?
Yes, sir.
Yeah. My audio is clear, sir?
Yes, clear, sir. Audible, sir.
Right. Thank you. So this is a 5-day international faculty development program on applications of mathematics in various fields with innovative approaches, and a very good initiative from the Department of Mathematics, Bapatla Engineering College. So now today I am going to deliver a lecture on Introduction to Mathematical Ecology. So before going to this one, the ecology, what is meant by an ecology and ecological systems, how this is related with our differential equations, and we will see some of the models what we learned in our engineering mathematics and what is the gradual development of this one. I'll give 40 minutes of lecture on this one, right? So ecology is a branch of science. It includes human science, population, community, ecosystem, and mainly we are going to talk about the ecology ecology means it is a branch of science, and mainly we are going to dealing with about the population densities. That means if we have a particular system of population, whether this population is being a human population or an animal population, and whatever the population, how this population is going to serve over a period of time. So that is the most center point of this ecological system, and this is the a real life problems. That means when we are having a system, that means when a human system or an animal system, that system, how the system is going to behave over a period of time. Suppose this system, let it be n. N is the system of the population, whether that population may be a human population or an animal population, whatever, a plant population, everything deals under ecological system. So this is meant by an ecological system. This system is how the system is behaving over a period of time. It is not that much of easy to understand this much of this system is behaving over a period of time. How this is not that much of easy. When we are having a system, when we are having a system of population, there are so many effects are involved in the system. So there are so many effects. When a system is there, suppose there is a population system, the density of the population depending upon so many factors. Whether this system having some food is one factor. If the food is not sufficient, food is available, then there is effect on the system over a period of time. Suppose this system having some habitat effect. So this habitat effect means some space effect. So when there is no sufficient space to evolve that particular species or particular population, that effect is also there on this density of the population. There are climate changes are there. So there is a flood, there is an earthquake. At that time of also the system may be changed over a period of time. So when we are going to take one model for a system, then that system involves so many factors we have to consider. So like that, sir, are you getting my audio, sir? Hello.
Fani garu.
Sir.
అక్కడ పార్టిసిపెంట్స్ దగ్గర క్రాస్ ఉంది కదా, అది క్లోజ్ చేసేయండి. రైట్, ఓకే
సార్. నేనా సార్? ఓకే,
ఇట్స్ ఓకే నౌ.
రైట్ సార్. సార్, ఆర్ యు గెటింగ్ మై వాయిస్, సార్?
ఎస్, వినపడుతుందండి.
రైట్. సో దట్స్ వై when we are model a system, and that system over a period of time, that means how the system is changing over a period of time. In our calculus part, we are going to take this as dn over dt, the rate of change of the system over a period of time. We are taking the rotation as dn by dt, the rate. So when we are considering this, we are considering the system only with respect to the time. But in some cases, the system does not depending upon the time. There are so many other factors are also involved with respect to time, with respect to space, or with respect to some other independent variables are also there. So to model that type of system, we are using the partial differential equations. having one independent variable and there are so many one dependent variable, there are so many independent variables are involving when we are modeling that type of systems. We are using the partial differential equations. Now for this model in ecology, I am going to confine, we are having only one system of dependent variable with respect to over the time, that is a single variable, single independent variable, that is t. So I am going to concentrate on only the ordinary differential equation. That means what I am going to say, when we are going to model an ecological system, first we have to understand how the system is behaving with respect to many factors. And if we are having so many factors we are involving, then we can model by using the partial differential equations. When I am going to constrain the system is over a behaving with respect to the time, that we are going to deal with the ordinary differential equations. So when the system is behaving over a period of time, that system is called a dynamical system. That system is called a dynamical system. So the dynamical system is the system having a over period of time, how the system is going to change. So when we are observing the system, suppose there are mainly when we are observing, suppose with respect to the time, suppose I am going to take the system n, that is the density of the population over a period of time. So the system, suppose the population starts here, the system is
Pani garu, participants, please wait for a minute. There is a power problem. I will get back to you soon. Please wait for 1 minute.
मुले जे ड्रॉपला गेले ना
All the participants are requested to please wait. Some technical issue, please wait 1 or 2 minutes. The resource person will come back within 1 or 2 minutes. Thank you, participants. Dear participants, please wait.
Karunakar sir. Karunakar sir.
Okay, Masharu, we'll start the session.
Sir, Pani sir has some power problem, so we start now the second session, and later he will come and join with us. Please go ahead, sir. Pawan sir, 1 minute, sir.
Yeah. Sir, na screen share అవుతుందా?
Very clear, sir. Very clear.
నాకు కనిపించడం లేదే. So which screen you are getting now?
So I am seeing, sir, 115217319 ABC using dot product.
So, do you want me to go through the papers or how can I? Because I am not getting that. Okay, maybe.
1 minute, sir. I think there is a technical problem. We will contact you immediately. TSR, sir, please make a call to Pawan, sir, sir.
Pawan sir calling.
Sir, please, sir, Pawan, sir, please put your audio in mute, sir. Few minutes.
Yeah, yeah.
Sunita, madam, put your audio mute, please. So, dear participants, I am extremely sorry for the inconvenience caused by power failure and technical issues. So now we are going to start the session. Karunakar, sir, please go ahead, sir.
Now the second session, it is enriched with our the second lecture, applications of linear algebra in machine learning, given by our other resource person, Dr. C.V. Pavankumar sir. Really, we are thankful to you for extending your valuable support, even the timings are inconvenient to you. Now I request one of our staff organizers, Ms. K. Sunita, to present profound profile of Dr. C.V. Pavankumar Garu.
Good evening all. Welcome you all to a 5-day international faculty development program on applications of mathematics in various fields with innovative approaches. It is my privilege to introduce today's dynamic resource person, Dr. C. Venkata Pavan Kumaru Garu. Dr. C. Venkata Pavan Kumaru Garu is a senior faculty working in Apex Max Excel Center, North Carolina in USA. He did his MSc in Applied Mathematics from Sri Venkateswara University, Tirupati, post-graduation diploma in Operation Research from Pondicherry University, and PhD in Mathematical Modeling from Jawaharlal Nehru Technological University, Hyderabad, under the guidance of Professor N. C.H. Pattavi Ramacharya Garu, retired Professor NIT Warangal. He has published 18 research papers in various reputed international journals. Presently, Dr. Pavan Kumar Garu working in the area of mathematical modeling. Dr. C. Pavan Kumar sir has got good reputation among students for his best way of teaching for the last 2 decades. His simplicity, good attitude, teaching abilities, research capabilities, and presentation skills are additional qualities in him apart from his goodness and vivid experience in the field of education and research.
Thank you, Sunita, for your nice introduction about Dr. C. Pavan Kumar Garu. Now I hand over the session to Dr. C. Pavan Kumar Garu. Dr. Pavan sir, please start your session, sir.
Yeah, thank you, sir. Thank you for your valuable words. And respected faculty members, namaste to all. And thank you for giving me this opportunity to deliver a lecture on the memory of eminent professor Komarolu Chandrasekhar Garu. And thankful to head of the department mathematics KVL and Acharlu, earlier speaker Dr. Fanikumar, myself and Acharlu. We did PhD under guidance of eminent mathematician NCH Pattabhiramacharlu Garu. And I am the 42nd student under his guidance. And the thing is, I know that very learned faculty members are there in this session, but I will try my level best to give the best. Thank you. So the thing is, today I am highlighting some few basic concepts of linear algebra. Those are very important in understanding these few concepts of machine learning concepts. So usually the basic idea of multiplication is what we are going through all the textbooks is a general dot product. Like, for example, I think you are getting my screen now.
Yes, sir. Yes, sir.
Yeah. So yes, sir. Thank you for that. So this is what the title is called as big picture of multiplication. So the thing is, if you are doing 115, 1217 or 319 are the three rows of a matrix, and we are multiplying with ABC. This ABC is, they are called as weights. So if you are doing this multiplication, normally what we are doing 1 times A and 1 times B and 5 times C, that we are doing here like a dot product. That's what usually we are doing. But in another way, why can't we do the same matrix, treat these different columns of R3, three-dimensional, because it has three components. 1 and 2 are the three components. 1, 1, 1 are 1, 3 components. Like this is a vector in R3. And these three columns, why can't you take this weight A and multiply the first column, take this weight B, multiply the second column, take this weight C and multiply the third column and add them up. We will get the same result. See that? Earlier it was A plus B plus 5C. Now it is also A plus B plus 5C. So the normal dot product it gives the row-wise picture. This will give you the linear combination of vectors. So most of the time, linear algebra runs with linear combination of vectors. Like if the two vectors are there in that system, if you join them by multiplying one vector with A and another vector with B, so that's called linear combination, right? So the three columns and these weights is nothing but a linear combination of vectors. So now that's the understanding of columns. Now other thing is, why can't we multiply the row times a matrix? So this A is earlier one is a column I took on the right hand side. Now I am taking the same row on the left hand side. Now this A times the first row plus B times the second row and C times the third row will get the A times of 115, B times of 217. That's a row-wise linear combination. One is the column-wise linear combinations. The main problem is how the linear combination of columns is helping in solving the linear system like AX is equal to B. So I took the same three columns, 1, 2, 3, 1, 1, 1, and 5, 7, 9. And I want some weights which brings the vector 3, 4, 5. That's the total idea of the Ax is equal to B. The idea is I want some X, some Y, some Z to mixture all these three columns and produce 3, 4, 5. That's the linear combination of columns. So I am looking for such weights. X is 1, Y is 2, Z is 0, so that I will get 3, 4, 5. So solving the linear system Ax is equal to B is nothing but how columns are adding together to get the right hand side B. That's the thing. And the second thing is how it helps in solving Ax is equal to 0. It's a homogeneous system. Earlier was non-homogeneous system. So now I'm taking the same columns 1, 2, 3, 1, 1, 5, 7, 9 as three columns. And I want different weights which produces the right hand side 0, 0, 0. So the logical thing is if you take X is 0, Y is 0, Z is 0, you will get the right hand side is 0, 0, 0. But that's called, we are calling it as trivial solution. Does this system have any non-trivial solution? Yes, because the 2 times of 1, 2, 3, 3 times of 1, 1, 1, and minus 1 times of 5, 7, 9 will get 0, 0, 0, 0, 0 on the right hand side. Why this is happening here like that? So when we are discussing Ax is equal to B here, we took Z is 0, only 2 columns are very important to produce the 3, 4, 5. Third is not necessary because that we are telling with the reduced row echelon form. See, this 1, 0, 1, 0, 1 is identity matrix that is giving that only 2 columns are very important. That's called as pivot columns or linearly independent columns. There is no pivot element in the reduced row echelon form. And what does this 2, 3 is telling to us? So 2 times of first column, see that the 2 times of first column, 3 times of second column, and minus 1 times of this will become 0, 0, 0. So the thing is, what does this matrix do here? Let's say simple multiplication only. But if I'm multiplying with a linear transformation in a 2D, 1, 1 and minus 1, 0, I am getting by multiplication, final vector will be minus 1, 2. What is happening here? What does this matrix is doing here? What kind of physical phenomenon is happening there? That's the question. So input vector is transformed. This is the input vector in 2D. Is transformed to the other vector in the 2-dimensional minus 1, 2. But how it is happening? Is there any process in that? Or we are looking for what kind of linear transformations in between these two input vector and output vector? So first we need to understand what is meant by, to discuss about this, first we will understand what is shearing and rotation. So shearing is pushing a vector x comma y towards the right or up or down. Let's say this x comma y is a vector. We are pushing towards the right, that is x prime and y prime. But how much we are pushing that x to x prime? That distance is nothing but sy. So x prime can be written as x plus sy. Y prime can be written as just y, because the height is not changing from earlier vector to the next vector. So y is keeping like that y. Why can't we write this x prime y prime as a linear combination of columns? It's a system. So 1, 0 is first column, S1 is the second column, and xy is that. Or we can do in a same fashion. Why can't we shift this xy vector to up now, like that, to the vertical motion? So this is the another shearing matrices. So this kind of matrices, 1 S0 1, 1 0 S1 or 1 0 S1 like that, these matrices will produce shear on the diagrams. This is very important application in computer graphics, that why we are rotating, why we are sharing that particular image. Come to the point rotation now. So cos theta and sin theta and minus sin theta and cos theta are the two columns. Their determinant is 1. And if I'm plugging theta is equal to 90 and take that input vector 2, 3, what I'm plugging here, it gives minus 3, 2. Means it rotates. And the other thing is, this matrix is an orthogonal matrix. So what does orthogonal matrix will do? Orthogonal matrix will do rotation. So that rotation is 90 degrees rotation here towards the counterclockwise direction. So the input vector 2, 3 is rotated to the 90 degrees counterclockwise direction. We are getting minus 3, 2. So what is happening here? Do we have rotation and shear? Yes. So take 2, 3. This is the rotation matrices like that. See the same thing, 0, minus 1, 1, 0. So first applying the rotation and then shear, we are getting the final 1, minus 1, 2. So this linear transformation, doing first rotation, next shear to get this one. Why this is so important here, this shear and rotation matrices? Because to understand the big linear system, linear transformation, if you decompose into two matrices, that will be very easier to understand what is happening in the pictures. Or if you are looking into some computer graphics kind of thing, what is happening to the so-and-so vector. So this is first rotation is happening and shear is happening. Let me see something else. Rotation by shearing. So this is the rotation matrices. Why can't we write all the rotations into 3 shears? Yes, we can do that. So cos theta and sin theta minus sin theta cos theta is a rotation matrix. That rotation matrix combined into 3 shears, like 1 minus tan theta by 2 and 0, 1, 1 sin theta 0, 1, 1, 0 minus tan theta by 2 and 1. What is this in functions? It's a f of x going inside of g, the total g f of x is going inside of h. So this is the shear, that shear is going here, this full set is going there, so that we are getting all the rotations. So for example, if I am plugging theta is equal to 90 in whole the above 4 matrices, so this one becomes 0, minus 1, 1, 0. This one becomes tan 90 by 2 is tan 45 is minus 1. So like that I got 3 matrices. This is called matrices decomposition. So one big not understandable system can be converted into 3 pieces. What is this piece? Shear to the left. See, if you apply 2, 3 to this matrix, we will get minus 1, 3. 2, 3 shifted to the left, minus 1, 3. See that? 2, 3 is shifted left by 3 units. Where is that 3? The 3 comes from here. So 2, 3 is a vector shifted to the left. The same vector shifted to the right and then shifted to the left, so that we are getting theta equal to 90 degrees matrix. So that's the thing. Other thing is very important aspect in linear algebra is linear combination of vectors. So why does this linear combinations is important? So you have some vector 1, 1, you have another vector 2, minus 1 here. Let's say v1 and v2, something like that. If you extend this is 3v1 or this is minus 2v2, not only like that, so what is this one? What is this green one? This is a subspace of R2. This is a subspace of another subspace of R2. So 2 subspaces, very important point is that this is a subspace. The subspace means if you take a vector, multiplying with 0, you will get 0, 0. If you multiply some number, it will stretches. If you are multiplying with negative number, it will go back. So always if you do any scalar multiplication, it stays there. It is staying there. So it's a subspace. Same thing like that, this is also a one subspace. So these 2 subspaces will produce any vector here in this system. So it's a new coordinate system, not like x-axis and y-axis. You can do these 2 as 2 axes, moving 1 unit, 2 units, 3 units. moving -1 unit, -2 units, -3 units, and reach any point in this. Why we are able to reach any point in R2? Because of these two. Because we have two directions. If we have only one direction, we can't reach that point, any point. So to reach in R2, we need two different directions. Therefore, these two are linearly independent. So linearly independent is saying that how many different directions are there and what kind of vector we can reach. That is the idea behind the linear combination of vectors. See, this figure is not that much comfortable, but if I'm bringing this to a perpendicular linear combination of vectors, this is more handy. Linear combination of orthogonal vectors is easy to understand. See, instead of x and y-axis, just we are turned a little bit. So the beauty of the orthogonal vectors is we can say if they are orthogonal, directly we can say that they are linearly independent. Not necessary to check. So if the two orthogonal vectors are there, they are linearly independent. So there orthogonality comes. So you have some vectors in R2 and R3, two lines through the horizon. This one is U, this one is V. So the distance between these two is U minus V. This distance between, this is a minus V vector. This is V, this is minus V. So the geometry of this is, from this U, the distance of V and distance of minus V should be same. So U and V are said to be orthogonal. If they are orthogonal, the geometric point of view is this distance and this distance should be the same. So distance of U comma V and distance of U comma minus V should be same. This is same as requiring, so if you take the distances, I am taking the squares, because squares is more easier, because I can write it as dot products. So U plus V whole square is equal to U plus V dot U plus V. And I am expanding, distributing that dot product. And U dot U is the length of U square and 2U dot V. And distance of U comma V whole square is same thing. We are saying that these two distances are same, therefore these two expressions are same. So 2 times of UV and equal to minus 2 times of UV, this is only happening when U dot V equal to 0. So U dot V equal to 0 means it's a condition evolved from this geometry, because the distance of U minus V and distance of U plus V should be same. So the orthogonality condition what we are using is U dot V equal to 0. If two vectors in any, like R2 and R3 and Rn, orthogonal if U dot V equal to 0. Why that orthogonality comes in big picture of linear algebra? So what is these 4 spaces? Before that, just take one example, 1, 2, 1, 2, 1, 3 and 3, 3, 4. This is easily understandable matrices. Add these two, you will get this. 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 3 equal to 4. Therefore, this vector is a linear combination of these two, one time of this and one time of this. We are getting this. So this is a dummy one, or this is cooked up from these two columns. So the reduced row echelon form is saying that only 2 by 2 matrix is here, 2 by 2 identity. It's saying that rank is 2. If rank is 2, there is no pivot element. These are all called as pivot elements. So there is no pivot element, therefore this is called as free column. These two are called as linearly independent columns. So now what is row space? What is row space here? So 2 rows are there, 1, 0, 1 and 0, 1, 1. Take all their linear combinations. One more time. Linearly, these are the 2 rows, 1, 0, 1, 0, 1, 1 are the 2 vectors. If you make a linear combination of all these 2 columns here, all these 2 vectors, you will get a row space. because it's a dimension is 2. Why dimension is 2? Because only we have 2 rows. So dimension is 2, or 2 elements in this row space. So dimension is 2. Now, see that if you do that, all linear combination of these 2 vectors, we will get a row space. Similarly, we have 2 linearly independent columns, 1, 2, 1, 2, 1, 3. Take these 2 as a column space, because these 2 are the only linearly independent vectors. That dimension is also 2. Other thing is, the null space is -1, 1, 1, -1, -1, 1. Why this is null space? If you multiply this vector with -1, -1, and 1, you will get 0. Because -1 of that, -1 of this column, and 1 of this. Already we said that 1 time of this, 1 time of this is this. So if I am plugging -1 and -1, -1 and -2 will become 3. -2 and -1 is -3, and +3 is 0. So if I am taking -1, -1 here and 1 here, write a linear combination, we will get a 0, 0, 0. Therefore, it's a null space. Null space means if you multiply with -1, -1, 1, you will get whole set of vectors. Like that, what is A transpose? This is the A transpose. Similarly, you can calculate the null space of A transpose. So now, what is this? This is a big picture of linear algebra. So these 2 are, one is row space, whose dimension is R, and null space is this line. These 2 are perpendicular. So any vector in row space and any vector in null space should be orthogonal. Similarly, a column space means you take any linear combination of these 2 vectors, it's a column space, and null space of A transpose, these 2 are orthogonal complements. Means if you take any vector in null A transpose and take any linear combination of columns in column space, we will get 0. They are orthogonal. So if A is an m by n matrix, orthogonal complement of row space is a null space of A, and the orthogonal complement of column space is null space of A transpose. Sorry, I did some error here. So the column space of A is null. Column space is null space of A transpose. Okay, and the thing is, there are 2 observations here. So linear combination of columns from row space. Row space is 1, 0, 1 and 0, 1. So take 2 times of that, 3 times of 1, and take null space of this, 2 dot product, you will get 0. That's the condition. So any vector from row space, any vector from null space, they are orthogonal. This will be used in very, very, very important application of this one is the singular value decomposition in machine learning. So that I will try to discuss later, why this point is very important in singular value decomposition. So a matrix will be divided into 3 parts. One is orthogonal matrix, second one is the diagonal matrix, third one is also a orthogonal matrix. For that decomposition, this is the very, very, very important concept. The second observation is similar to that. Take linear combination of vectors in column space and take linear combination of null space of A transpose, do their dot product, that dot product is equal to 0. This picture is very, very, very important. So, and the underlying concept is that is the rank nullity theorem. What is the rank nullity theorem here? So dimension of row space plus dimension of null space is equal to number of columns of matrix A. See here, what is dimension of row space is 2, dimension of null space is 1. If you add, that will become 3. That are 3 columns here. Very, very, very important. Next, the thing is orthogonal sets. What is meant by an orthogonal set? The set of vectors, there are some p vectors, or u1, u2, u3 and up in r power n. In r power n means it has n components. Is said to be orthogonal set. Each pair has to be orthogonal. means u1 dot equal to 0. Take any two vectors, u1 up, their dot product is 0, u3 up, that their dot product is 0. Take any two vectors in that set, their dot product should be 0. That kind of vectors is called as orthogonal set. What is the advantage of that orthogonal set? If I'm having orthogonal set, we can say they are in different directions, therefore they are linearly independent. So if is orthogonal, non-zero vectors in R power n, S is linearly independent, and hence it works as a basis for the, because these are all having different directions, that works as a basis of subspace spanned by S. You can take all linear combinations of this, you will get that subspace. What's the advantage of doing this? So u1, u2, up are orthogonal basis for the subspace of W in of R power n. Then each vector Y in W can be written as a linear combination of vectors. So take any vectors from that subspace. W is a subspace. Take any vector from that W, that is Y. Y can be written as linear combination of these orthogonal vectors. So how can we get that C1, C2, C3? Because whenever writing a linear combinations, the constants are very important. How can we get that? Because these vectors are mutually orthogonal. Take dot product of u1, y dot u1. Therefore, u2 dot u1, u3 dot u1, up dot u1 will become 0. Only this will be remaining if we are doing dot product. So u dot u1, sorry, y dot u1 is nothing but c1 times u1 dot u1. If I am dividing with the u1 dot u1 there, you will get the constant c. One more time, y dot u1 is equal to c1 times u1 dot u1. That u1 dot u1 I am writing on the other side. Therefore, any constant I can find out, ci is equal to y dot ui by ui dot ui. Let me take one example. So 3, 1, 1, minus 2, 1, minus 1, 2, 1, minus half, minus 2, and 7 by 2. These three are orthogonal. Let me check that. 3 minus 3, and 2, and 2, 3 minus 3 is 0. Yeah, it's a pairwise orthogonal. So these form a basis. Take any vector from R3. Just I took some vector 6, 1, minus 8, because this is in R3. How can I write this 6, 1, minus 8 as a linear combination of these u1, u2, u3? So how can I get this 1? Is y dot u1 by u1 dot u1. This minus 2 is coming from y dot u2, because y is known to me and u1, u2, u3 are known to me. This calculation is very easy. So that getting these weights, the linear combinations, the constant is y1, y dot u1 by u1 dot u1, so that we are writing y as a linear combination of three vectors. That's the advantage of having the orthogonality. Now, what is the orthogonal projection? So projection is that if you have one vector y and there is another vector u in R power n, in Rn, this vector is very closest to this one, because this y vector has to drop a perpendicular here. We are calling it as y hat. That y hat is a some multiple of u. We are calling it as alpha u. And what is z here? Z is, this is y hat, this is y minus y hat. If you add these two vectors, you will get y. So this is y hat, this is y minus y hat. So if this g is equal to, we are calling it as y minus y hat. Let me do some idea of how we are getting this projection alpha. So the major idea is how to find this alpha. So z is orthogonal to u, z is orthogonal to u. So if z is orthogonal to u, z is nothing but y minus y hat. So y minus y hat is orthogonal to u, therefore their dot product is 0. But y hat, we are calling it as alpha u, because it's a multiple of u. So in y hat, I am substituting alpha u and do dot product. So the same thing what we did in the last case. here we are doing the same thing here, but for one case. Earlier we did for 3, now it is a one thing. So y dot u by u dot u is alpha. You plug that here because this is called projection. In place of alpha, we are plugging that. So this is all projections. This is a projection, this is a projection, this is a projection, alpha values. Now, how projections helps in understanding the earlier fact? Yes, see that. This is the y, this is a projection y2 hat, this is the projection y1 hat. If you add y1 hat and y2 hat, because this is a triangle of vectors, therefore we are getting y. So y is equal to y1 hat and y2 hat. Y1 hat is this one, sorry, y1 hat is this one, y dot u1 by u1 dot u1 times u1, y2 hat is this one. That is the fact. So the observation is, if a S is u1, u2, u3, up is orthogonal set, the orthogonal, it works as an orthogonal basis to W, which spans W, then any vector y in W decomposes into sum of P projections. Where is that P projections? On U11 projection, on U21 projection, on U3, like that. There are P projections. If you are adding them, you will get y. So sum of projections on mutually orthogonal vectors will produce the y, will produce any vector in W. So this theorem is another important concept, that's orthogonal decomposition. This is simple one. So orthogonal decomposition is nothing but one is in the direction of y hat, one is in the direction of z. So these two are orthogonal now. These two are orthogonal. If I'm having y information, I can create these two. Like physics, if you have a force, we can call it as f cos theta and f sin theta. The same idea we are using in orthogonal decomposition. So now y hat the projection of y on w. This is a w is a subspace. We are taking y vector which is not in that subspace. How can I write this y as a orthogonal decomposition? We know that y hat is a linear combination of that perpendicular vectors u1 hat, up. These are the weights. So we are getting y hat. But we know that z is y minus y hat, this one. So simply y hat is, I am plugging that. So this is orthogonal decomposition. If I am adding these two, I will get y. This is y minus y hat and y hat. If I am adding these two, I will get this y. That's called orthogonal decomposition of vectors. This is very important in one phenomenon called as Gram-Schmidt process that we are going to discuss in few minutes later. So properties of orthogonal projections. If u1, u2, up is an orthogonal basis for W, and if y happens to be in W, then projection of y is nothing but y. The thing is, what this statement is meaning is that if y is sitting here, not in some other, y is sitting in W, for y itself is a y projection. Because y is sitting here, y hat and y will become same. That's the idea. If y is not in that W subspace, we can decompose. If y is in that subspace, y hat and y will be the same. So this is the best approximation theorem. This helps us in doing line of best fit. So best approximation theorem is, let W be a subspace of Rn. This is a W, subspace of R power n. Let y be a vector in R power n. See that y is a vector in R power n. My question is whether y is having a projection y hat is nearer or another vector is near to that y. Which one is the best one? Do I need to take y hat or do I need to take v? So to decide that, the question is y hat, the main idea is y hat we are calling it as very nearer one because it's a perpendicular one. Why can't another vector v? Is there any possibility or not? That we are checking here. So the best approximation theorem tells us W is a subspace of R power n, Y be any vector in R power n, Y hat is the orthogonal projection of Y onto the W. Yes, Y hat is the orthogonal projection. Then Y hat is the closest point on W to Y. Y hat is the very closest point on W to the vector Y. So in sense that, so Y minus Y hat, this is the distance between Y and Y hat. This is the distance between Y and other vector. That Y minus Y hat is always less than Y minus V for all V in the W, in the subspace W. If you take any vector, that Y minus V is always greater than the distance between Y minus Y and Y hat. So the vector Y hat is the closest best approximation of Y by elements of W, because take V in W distinct from Y, distinct from Y hat, I am taking V on a subspace. Y hat minus V, if you plug Y hat minus V, that is in the subspace. Because Y hat in the subspace, V is also in the subspace. Any linear combinations should stay there. So Y hat is in subspace, Y hat is in W, V is in W. If you take differences, because it's a linear combination, that has to be in that subspace. So Y hat minus V is in W. By orthogonal decomposition, Y minus Y hat is orthogonal decomposition. Therefore, these two are perpendicular. So Y minus Y hat and Y hat minus V are perpendicular to each other. Their dot product is 0. We can apply some Pythagorean principle and we will get that condition. So this is the best approximation theorem. Why? Yeah. So now these two are the orthogonal vectors. U1, U2, UP is an orthogonal basis for a subspace W. Then projection can be written as, this is a, because I am calling it as orthonormal, the denominators U1 dot U1 will become 1. Therefore, I am removing that. So there is a more advantage with the orthonormal vectors compared with the orthogonal vectors. So if a basis is orthonormal, your calculation will go easier. The denominator won't come, that U dot, you not necessary to come, because that denominators will become 1. That's the whole idea. So now projection, if we are having like this, that we can write it as U transpose Y. This is a very important application for calculating the projection of Y in a given subspace. So I'm doing one simple example here. So W is a subspace of R cube. So I'm taking one subspace, two linearly independent columns. So they are orthogonal because I'm taking their dot product, 1 times 2, 2 times 2, and that will become 4. 2 minus 2 is 4, negative 4, that makes 0. So they are orthogonal. I'm making them into orthonormal. So now this is an orthonormal basis. This is an orthogonal basis. This is an orthonormal basis. So I am taking U times U transpose. I am getting some 3 by 3 matrix. Take any vector Y equal to 1, 1, 1. Take any vector 1, 1, 1. That projection is this one. So 1, 1, 1 multiplied with U transpose this matrix, you will get that Y hat. So to find out the projection, this is the very important formula, U transpose Y. And by orthogonal decomposition, we know that earlier we did that some calculation Y hat here, 7 by 9, 11 by 9, 8 by 11, sorry, 8 by 9. And if you are subtracting from Y minus Y hat, this is orthogonal decomposition. This is Y minus Y hat is perpendicular to U1, is perpendicular to U2, and Z is perpendicular vector spanned by U1 and U2. So this vector is Z, that Z is perpendicular to, yes, perpendicular to U1, this vector, because that's the orthogonal component, and perpendicular to the second one. Or you can take any linear combination of these two vectors, that Z should be perpendicular. That's more important. The other thing is, yeah, This is the very important concept of how to create an orthogonal basis. If I'm having one basis to the system, they are not orthogonal, but how can I create an orthogonal basis? That is the more basic idea of this thing. That's called Gram-Schmidt process. So take some two vectors. We are calling it as first vector as V1. Take V2 as X2 minus P. What is that P? P is the projection of X2 on X1. The same thing. So Gram-Schmidt process is, if you have P perpendicular vector, P orthogonal vectors, orthogonal basis, U1, U2, U3, and UP, this is the process to find out the orthogonal basis. Why this orthogonal basis is important, that we are going to discuss in SVD, singular value decomposition. V1 is X1, V2 is X2 minus, same thing, this is orthogonal component. This is another orthogonal component. This is another orthogonal component. Just it's a going by repetition of orthogonal projections or orthogonal decompositions, we will get this process. The next important thing is QR factorization. Yeah, let A is an M by N matrix with linearly independent columns. Then A can be factored into QR. That's the main motto of the linear algebra. Is there any factors of a matrix? QR factorization. Q is orthogonal. R is a diagonal upper triangular matrices. What does that upper triangular matrices will give us? What Q will give us? That's the whole idea of the earlier discussion. So now, what does this matrix do? This matrix A, if I am applying to the some vector, if I am applying this, what is happening there? So A is decomposed into Q and R. Q is orthonormal vectors, therefore these are the orthonormal vectors. How we are getting this one? This is coming from, this orthonormal vectors is coming from Gram-Schmidt process. We are using this technique and we are getting this information. Then what is R? How we are getting this R? Let's see. I will explain a little bit later this one. First, we will go to the geometrical importance of this constructing the orthonormal basis using the Gram-Schmidt. How can we understand this geometrically, Q and R? The geometrical importance is orthogonal matrix which rotates and upper triangular matrices. See that this R is having some diagonal elements and some elements are sitting here. What is this Sx and Sy and Sg? So this matrix can be decomposed into three matrices like 1, 1, Sz, means it's a stretching factor along the z-axis. This is the stretching factor along the y-axis. This is the stretching factor along the x-axis. See, Sx is sitting here. Remaining is, instead of 1, 1, 1, Sx is sitting here. Instead of 1, 1, 1, Sy is sitting here. The second one is stretching along the y-axis. So, if you are having identity matrix, no stretch is there. If it is having some number instead of 1 here, that is the x-axis stretch. This is the y-axis stretch. This is a stretching along the z-axis. Yeah, now there is 1, 1, 1. These are the shears. Earlier what we have discussed. So the R is having the full of information of stretches and shears. So along the x-axis stretch, y-axis stretch, g-axis stretch, and shearing along the three directions. How much it is turned, the diagram or whatever the input is, your picture is shearing towards the g direction or shearing towards the y direction. These three elements will give us, the shears. So that's the advantage of decomposition of matrices. Now, this is how we are calculating that QR decomposition. I think that's not important. I will skip this process. Then we will go to the, how we are going to get the R matrices. We are decomposing A into an orthogonal matrix Q.
Sir, I have a doubt, sir. Do you have any graphical representation for the previous one, sir? Can you give any graphical representation for the previous one? A equal to QR.
So this is I collected from the some textbook. I will give the name of the textbook if you want later.
Okay, fine, sir. Thank you, sir.
Yeah. This is stretching factors, all these three stretching factors and shearing. I have some textbook. I will inform to you later. I will give the details of that.
Okay, fine, sir.
Thank you, sir. Thank you. And to find R in QR factorization, how we are getting that R? A is a orthogonal matrix. R is we have to find out now because we have Q from Gram-Schmidt. And if you are taking Q transpose, because that's the advantage of orthogonal matrices. Q transpose Q is equal to I. So R can be cooked up from Q only and A only. Known information is there. So R is coming from the known information. Therefore, your calculations will become easy to get the R. Now, this will comes in least square problems. So what is the least square problem? What is happening in the least square problem? Inconsistent systems arise often in applications like AX is equal to B. In many practical applications, the system is not consistent. How can we solve that? The best way of doing is projections. So B has to be projected on a subspace that the best we can do is to find out some X. We are finding X values. We are finding X values means nothing but the weights. These are the columns. X means weights. I need to cook up that linear combination of vectors. That linear combination of vectors, I need to produce B. But B is not getting. I am not getting that B. How can I get that B closer to B now? That's the idea of projection. So now, the best one can do X that makes AX is as close as possible to B. So simple, it's a linear combination of vectors. How we can get the B? If you are not getting the B, closest B. So what is that closer one? Think AX as an approximation to B. The general least square problem is to find out such X. You have to find out X. The distance between B minus AX is small as possible. So the AX will give you B, but not B, how close these two are. How close they are. This is telling us how closeness. So the is a square root of sum of squares. In statistics, the distance of this distance is called a sum of squares in statistics. Okay. So the solution to let me complete this one. The vector B is closer to, already we did that. Best approximation theorem tells us AX is the very closest one to B, not this V that already I discussed earlier. So B is the closer to AX hat. Then A is M by N, B is in R power M. The least square solution AX is equal to B is an X cap. We are calling it as a separate name for that. X cap, that B minus AX cap should be. This is nothing but what I'm telling is the whole idea is nothing but just I am replacing V with AX. Earlier I did that. That's called best approximation theorem. In place of V, just I am writing AX. The idea is same. That's the connectivity of this and earlier statements. So A is an M by N, B is in R power M. By best approximation theorem, we applied the B as a projection. So we are calculating B hat. See, the B hat is projection of B. How can we get the projection of B? That already we discussed U transpose times Y. Earlier I discussed that. So AX is equal to B hat is nothing but orthogonal decomposition. So by orthogonal decomposition, B minus B hat is perpendicular to each column of A because it's a column space. It's a column space. Earlier we took it as W as a subspace. Now because A is important here. Therefore, the column space comes here. So the column space of A perpendicular to each column of A. Let's say AJ. AJ is some column in A. Therefore, if they are perpendicular, their dot product is 0. Dot product can be written as transpose of something like that. So B hat is perpendicular to A1. So I can write it as like that. So A transpose is, so these are all the vectors in A transpose now. Because A1 transpose, A2 transpose, AJ transpose, or it's simply we call it as A transpose. Instead of writing so many equations, I can combine into a single notation, because columns are in A transpose, columns are A1 transpose, A2 transpose, and AJ transpose. Therefore, that is equal to 0. This we call it as, if you distribute this A transpose B minus A transpose A into X hat is equal to 0, and A transpose A X hat is equal to A transpose B. This is called as normal equations of the line of best fit. So if you want to calculate X hat, take the inverse of A transpose A on both sides, you will get the X hat. So this is the what we call it as normal equations. Let's do some simple example. I think we discussed some of these concepts. Yeah. Let me see. Yeah, this one. Yeah. A is equal to 1, 2, and 2, 4. There is some danger here because these two are linearly dependent. They are linearly dependent, 1, 2, and 2, 4. So, 1, 2, and 2, 4 will give you only this line. If you take any linear combination of vectors, that stays there only, all linear combination. So, that's the subspace. There is another different vector B. Is that solvable? No, because this B is not in that space. B is somewhere else. So, it is not solvable. This inconsistent system. Let me do it one more time. 1, 2, and 2, 4 are in not different directions. If they are in different directions, their rank will become 2. Now I am having rank 1. Only one vector is there because one is the multiple of the other. So if you take all linear combination of these columns, they will sit on this line. So that is the subspace. And now we are calling it as column space because this whole line is generated from the linear combination of columns. Okay? And then I am looking for the solution for B, which is not in that column space. So this is an inconsistent system now. So how can I get a solution for B? So B you project on that, B hat. That's the B hat. That B hat is sitting on that line. Take that B hat as a instead of B. Now we will get the solution. Let's see that whether it works or not. Yeah, I don't want to do this one. This is enough. So the normal equations are A transpose AX is equal to A transpose B. Like earlier statement, this is the main formula for that. So we are taking that A transpose A. These are the normal equations. This is the A transpose A calculations and XY. This is A transpose B. This is A transpose is 1, 2, 2, 4. A transpose A is 5, 10, 10, 20. That all calculations is easy. Now this is normal equations. If you solve this system, very important. Because again 5, 10 and 10, 20 are sitting in a same, they are linearly independent, so not invertible. So how can we do that? So now 5, 10 and 10, 20 and 7, 14, see that 5, 10, 7 and if you are doing some R2 minus 2 R1, this will go 0. 5, 10, 7, it's multiplied by 2, 10, 20 and 14. So this row is not necessary. This row is cooked up from that row. So now this will have infinite number of solutions. So how to solve that? Yeah. Now next is my thing is, where is that minus? Yeah. How to solve this inconsistent system that I took minus 1, 4 here. Yeah. That's the thing. I took the projections. Projection is 7, 5 and 14, 5. That projection is sitting here, B hat. Yeah. Now I take instead of B hat I am taking. Now I got the solution. There are infinitely many solutions. That's the whole idea. Next. Rotation matrices in 2D and 3D. Because why I'm focusing into the rotation and shearing? Because all orthogonal matrices will produce some rotation. So now this is the 2D matrix. If you apply some x and y to that matrices, so you will get x cos theta and minus y sin theta and x sin theta and plus y cos theta. So now these are all orthogonal. Let's come to 3D. cos theta and sin theta. Rx is, this is simple normal thing. R transpose is equal to I because this is orthogonal matrices. R transpose is equal to R inverse and the determinant is 1. So 3D rotations about x-axis, this is the matrix. Y-axis, this is the matrix. So what is happening here? If I am taking RZ90, if I am taking RZ 90 degrees here, so if I am taking the vector 1, 0, 0, it will shift to the 0, 1, 0, means it is rotated to the y-axis. 1, 0, 0 is sitting on x-axis. This is a unit vector in x-axis. If you apply that, this transformation, it will rotate to 0, 1, 0. It shifted to the y-axis, means the elements, those are sitting on x-axis completely turned into the y-axis, right? That's the orthogonal, because it's orthogonal rotation. So this matrices all creates orthogonal, means if you take the vector in z-axis, it turns to the x-axis in a, that's called right-hand rule, something like that, right-hand rule. So if you are taking to the x-axis, it will come into the y-axis like that. So 3D rotation, and if you multiply these three, what will happen? So there is, you can create ample of rotations by multiplying these three rotation matrices. So now, this is called as very important in flight dynamics. That's called yaw, pitch, and roll. What is this yaw, pitch, and roll? The flight is moving upwards and downwards. That's called pitch. Roll is it rotating through the wings. That's called roll. This is pitch. Yaw is moving horizontal movement. So this combined rotation is called as intrinsic rotation, and there is separate new coordinate system is developed from this, from the perspective of aerodynamics. That's called Tate-Bryan angles. That I'm not focusing too much on that. But this subject develops on these three orthogonal matrices. The thing is, yes, the same thing. Nothing new. A equal to QR. And this thing is given matrix A is M by N matrix, linearly independent columns, A equal to QR. Instead of A, if you are plugging A equal to QR, you can get X, the unknown X value, solving how we can solve X based on QR decomposition. So QR inverse I am applying on both sides, R inverse and Q transpose, because Q inverse is Q transpose because they are orthogonal matrices. Yeah. The machine learning is having so many two branches, supervised learning and unsupervised learning. In supervised learning, linear regression and pattern recognition, gradient descents, ridge regression, polynomial regression. There are so many regressions back there. And unsupervised learning is clustering. In clustering, they are called as k-mean clustering, hierarchical clustering. So many methods are there. But I am focusing this into a linear regression. Yeah. This is the thing, linear line of best fit. These are the data values, and x1, y1, x2, y2, and x and yn are the data values. We are fitting a straight line beta naught and beta 1. Beta 1 is the slope and beta naught is the y-intercept. For this best fit, this gaps from the data value to the expected value is called as residuals. So main idea is to reduce the sum of squares of residuals. The same thing, how mathematics is teaching like that, but a little bit of difference is there in machine learning. They are calling it as all random variables, that random distributions are there for the functions f of x comma y, and t is a random variables. They are calling it as a bit different, but the idea is same. The whole idea is this one only. They are projecting into some other identically independent distributed copies. Like that, it's a bit, language is difficult, but the idea is same. The machine learning is mixing the statistics and math and some other computer science methodologies, but underlying concepts are mathematics, fully based on mathematics concepts. But now the predicted value, the main idea is to reduce the sum of squares of residuals. So predicted values, so what are the predicted values? If I am taking x1, if I am plugging on that line, that is the predicted value. These are the observed values. So I am looking for beta naught and beta 1. One is the y-intercept, other one is the slope. So you convert it into matrices now. So this one is coming from beta naught, beta naught, beta naught, and this beta 1 is removing, right? That x1, x2, x3, xn are the data values. And I want output values y1, y2, yn, the observed values. So again, I am using that normal equations from the linear best fit. So A transpose AX is equal to A transpose B. Using the linear regression for, yeah, how can we apply for the science experiment? The same thing. How can we apply for the science experiment? A simple school experiment. Assume that we have an object with a given weight of 2 kilograms. We have from Newton's second law, F is equal to ma. That mass is fixed, now 2 kilograms. So acceleration and force are changing. So F is acting on an object and is given by a mass times the acceleration. That is the formula, F equal to ma. Because the weight is fixed now, because we are calling it as 2 kilograms of weight, the force depends linearly on the acceleration, right? So now, if you are doing some experiment, let's acceleration is fixed into 1 meters per second square, 3 meters per second square. Measured force is like this. Measured force is like this. Oh, so how can I fit a best line of fit? Line of fit means F equal to ma we are fitting. What is that m value now? So now A is, earlier I gave this, A is always 1, 1, 1 and X values. X values are 1, 3, 5, 8, 10. And on the right hand side, I need to take the measured forces. B is this one. So use the A transpose AX is equal to A transpose B. Do some math and multiplication. You will get beta naught is this one and beta 1. See, whole thing is linear algebra here. A transpose AX is equal to A transpose B. That's the thing. Still I have time. Excuse me, sir. Hello, sir.
Sir, excuse me, sir.
Yeah.
Somebody unmute their mic, sir. Nothing else.
Sir, still I have time. Okay. So do I have still time?
So 10 minutes, sir.
Oh, thank you, sir. Thank you. So now here the picture of singular value decomposition. This is the whole what we have discussed. Everything will come for this singular value decomposition. A is an m by n matrix. We are making into 3 products of 3 different matrices. U is orthogonal matrix. U is orthogonal means it's a rotation. V is also an orthogonal matrix. And this sigma is some diagonal matrices. So we are doing what A is doing, we are doing with the 3 parts. We are decomposing that matrix A into 3 different parts. One is orthogonal, other one is diagonal, other one is orthogonal. So we are taking A as a one input matrix. Let me give one example. There is a document. There are so many documents like M documents. I am looking for different words in that documents. Word 1, word 2, word 3 like that. So document 1, document M. If I'm having that word, I will filled with 1. If that word is not in that particular document, that element will be taken as 0. The second one is, let's see that how Amazon and Netflix are doing. We have so many users. User 1, user 2, M users.
Sir, excuse me, sir. Sir, once again, can you tell me when we can take a 0?
Yeah, if the document is not having the word. If the document is having that particular word, you take it as 1.
Otherwise, it is 0.
0.
Okay, thanks.
Is that okay, sir? So that you can fulfill the whole matrix. We'll get some m by n matrix. Or user 1, user 2, user 3, so on, user m. And movie 1, movie 2, movie, like that, n movies are there. If the user 1 is watching that movie, call it as 1. If the user 1 is not watching that movie, you call it as 0. So it's a whole matrix is converted into 1, 0, 1, 0, 1 matrices. How this idea of matrix A is split into 3 factors. So U is left singular vectors. Sigma is a matrix of singular values. How these singular values are coming and what are these left singular matrices that I am going to discuss in the next sheet. So this is the diagonal matrix. This diagonal matrix is so important. Will come from eigenvalues. The non-zero these are all the non-zero values, but these are arranged from larger singular value comes first and smaller singular values comes next. Means it will give you the like a descending order. Like higher number will sit here, next higher number will sit here. That will give you some kind of sense that I am going to explain. Yeah, right singular vectors. So these are the 3 products. How can A can be written as like that? So m columns because it has r columns. This is the basic idea of the singular value decomposition. Yeah. Come to this point. This is the best factorization of the matrix. The factors will be orthogonal matrix, diagonal matrix, and orthogonal matrix. Yeah. See that this is a row space. The whole idea is this. Take one vector. If I am plugging that vector in A from the row space, it will match up to U1. So what is the condition here? A V1 is U1. I am taking a perpendicular vector V2. So this is I am taking 2 perpendicular vector in that space. Does it maps to the orthogonal? The orthogonality here will maintain orthogonality here by A? Most of the times not. One more time, that is the basic idea. So how can we get these orthogonal matrices from this row space? That's by Gram-Schmidt. The orthogonal basis we can get that from Gram-Schmidt process. So here to create an orthogonal vectors, Gram-Schmidt is very important. The second thing is how this orthogonality will maintain there by A. For this we need singular value decomposition. So the thing is V1 is a vector. A V1 is sigma U1 because it is that sigma 1 is the stretching factor. A V2 is sigma V2. Like that, yeah, I'm writing that AV equal to U sigma. Right? AV1 is equal to U1 sigma 1. AV2 is equal to U2 sigma 2. That's a diagonal matrix and this is a columns. So now the idea is singular value decomposition. AV is equal to U sigma. That is coming from here. AV is equal to U sigma. And apply V inverse on the right hand side. So because V inverse is V transpose because it's an orthogonal. So that is the A is equal to U sigma V transpose. That I tried to show something about that, this one, A sigma V transpose. And that, how I can get these U and V's and how I can get these sigmas. That is, if you take transpose, because A is U sigma V transpose, what is A transpose on the left hand side? Because if you take transpose of this, it will flip, right? So V transpose is V, sigma transpose and U transpose. Because of associate, matrix multiplication is associative, therefore we can take U transpose. That U transpose will become I because U is an orthogonal. So now these three factors will remain. V, sigma transpose, sigma and V transpose. That sigma transpose, sigma are the diagonal matrices. Therefore, the multiplication will become sigma squares. That's the whole idea of the SVD. The basic idea of the whole thing is depends upon the Gram-Smith. So this is the some calculation of SVD, and that's the thing. Yeah. Thank you, sir.
Thank you, sir, for your lecture on applications of linear algebra and machine learning. This is the time for a question and answer session. Because of his participation, anyone they are having a question and answers, so please post in the chat box. That is a Q&A box. Sir will clarify your doubts.
Sir, how SVD can be applied in machine learning?
Yeah, because SVD, singular value decomposition, machine learning is, we can analyze the data like that, right, sir? We have so many factors. Which factor is having more influence? Which factor is having less influence? Like, let me tell you an example that if I'm having some data about the movies, the user is watching more comedy movies, or user is watching any action movies. So how can I get that information? That from the diagonal matrix sigma values, sigma is more dominant that user and concept. The concept means it's a genre now. So genre is nothing but comedy, kind of comedy or something like that. Movies are different variations, are right? Some socio-fantasy movies or action movies, comedy movies. How can I get that connection between the user and the genre? Or how can I get the genre and what are the dominant phenomena? That's the, I think that's the idea we can do.
Yeah, thank you, sir. It was a very nice session, sir. I learned so many things from you. I heard you, which was very interesting for me regarding rotation. I need to know more things about that. So that's why I asked the in between geometrical representation. So
Yeah.
kindly put that textbook. And,
Yeah. This is the textbook, sir. Applications of linear algebra by Stephen Boyd.
Stephen?
Professor from Stanford. Stephen Boyd.
Okay, fine, sir.
Yeah.
I'll go to
Applications of linear algebra by Stephen Boyd.
Okay, sir. So is it possible to get this PDF, sir?
Okay. Do you want this PDF, sir?
Yes. It will be a short note for me.
Yeah. I will give it to that KVL and Acharya garu. Is that okay?
Sir. Okay, thank you. Thank you so much. If I need anything, I will directly contact you, sir. Thank you so much, sir.
Sure, sir. Sure. You are welcome.
Thank you, sir. And thank you, Arundhal, for your great response and valuable support. Now, we'll start our session. Please wait, sir. Dear esteemed participants, due to unexpected power failure in the first session, the two sessions are interchanged for conducting smoothly the program. On behalf of Mathematics Department, we appreciate your good patience and support which you have given to us. Thank you one and all for your kind cooperation. Now I hand over the session to Dr. Fani. Dr. Fani, sir?
Yes, sir. Yes, sir.
Please start the session, sir. Pavan sir, please close your window, sir.
Sir, namaste, sir.
Option. Hello. Hello.
Pani sir, it is audible, sir.
Sir, share option. Share option. Please give me the share option.
Okay, presenter cheyali pani sir. Anup Marega. Make a just Anup Marega.
Yes, sir.
So, Panikumar sir, on behalf of participants, we humbly request you.
Okay, Panikar, you are the presenter now. You can present your
Yes, sir.
lecture.
First of all, I am very sorry, sir. Unfortunately, here the power off, sir. So today only it happened. Sorry for the disturbance, and now I am going to continue. Thank you for all. So in the previous what I noted, sir, there is a system. That system is going to evaluate over a time period T, over a time. So this phenomenon, this system is called a dynamical system. So the dynamical system is nothing but the system is evaluating over a period of time. So if you are observing the particular, there are types of systems. Suppose we are having a system over a period of time. So the system is behaving like this. Suppose the system is behaving like this. Suppose if you are observing another type of system, so the system is behaving like this. If you are observing another type of system, suppose this is the system over a period of time, the system is behaving like this. So if you are observing in all these systems, the first system, if you are having the initial population, suppose let it be N0, after over a period of time, the system is going to end, or suppose if you are going to take this one, it is having some a stable system. It is having some stability. If you are observing the second phenomenon, suppose over a period of time, the system is behaving like this, that system is an oscillating behavior. If you are observing the system, the third system, over a period of time, the system is behaving like this. This identification of this system is very much difficult. So this is nothing but a chaotic behavior. So it is very difficult to observe and analyze this type of systems. And this system over a period of time, some stability is there, and this type of system, some oscillation periods are there. So finally, when we are modeling a particular system over a period of time, we have to observe many factors. What are the factors are imposing on this particular system, right? Now I am going to enter into our main ecological models. So before going to my lecture, so these are the important mathematical ecology books. So in this book, this is a good book, Ranjit Kumar Upadhyay and Sataluri R.K. Iyengar, Introduction to Mathematical Modeling and Kinetic Dynamics. And if anybody wants to read one more book here, this is also a beautiful book by Strogatz, Introduction to Mathematical Modeling in Ecology and Epidemiology. This Strogatz is also a very good book, right? So now I am going to enter into a single species model. That means I am going to confine a system having a single population. A single population model, so it is the rate of change with respect to the time, which is equal to mainly the difference between how this population growth rate. This is nothing but the growth rate of the population. The growth rate of the population depending upon the difference between the birth rate and the death rate. So this is the rate of change of population. This is first identified by the great mathematician Malthusian. This model is developed in the year 1789. So this model is called Malthusian growth model. This is the model by a first order differential equation. And when we growth rate is dn by dt, if we are going to take 1 by n, if we are changing dn over dt, so that means the rate of change we take it as delta n. If we are delta n, this is the rate of change over a period of time. If we are dividing with the total population, this is called a per capita growth rate. This is very, very important in population dynamics. 1 by n over d, 1 by n into dn over dt. This rate is called per capita growth rate. So the per capita growth rate dn over dt, if we are writing this as dn over dt, is equal to r times n, where r is nothing but the difference between the birth rate and the death rate. This is represented by r. This growth rate is called intrinsic growth rate. And if we are multiplying this one, this is what is the in our first order differential equation we are learning this model. That means the rate of change of population is directly proportional to the amount of the population present at that time. We are teaching our students in first order differential equation application. So we are going to take dn by dt, which is equal to some r times n. This r is called an intrinsic growth rate. So the initial population we are going to take it as n naught. This is the total initial value problem. So if we, this is a linear differential equation. If we are solving the differential equation, we are going to get n is equal to n naught times the exponential e power rt. So therefore, this Malthusian model is also called an exponential growth model. Growth model, or simply we call it as an exponential model. So if you are observing the geometrical figure, the geometrical nature of this Malthusian model, if this intrinsic growth rate is positive, then this is exponentially the population size, the density is become growing exponentially. If r is negative, then the population is going to decay and the over a period of time. If r is equal to 0, then the population is always some constant which is equal to the initial population n naught. This is the model which is developed by the Malthusian model. So it is developed by the Malthusian. It is in the year of 1789. But this is the first model in ecological species. It is a single species model. So here there are some drawbacks in Malthusian model. What are the drawbacks? The population is not growing exponentially in all ways. If it grows, then there are so many problems occur in. So there is a food problem, there is a space problem, every problem is there. So this should not grow exponentially. So these are the drawbacks of the Malthusian model. But this is the initial model, the species ecological model. But from this model, the mathematicians developed so many models by incorporating so many factors in the population growth, right? So in this population, in this Malthusian model, the drawback is the population cannot grow exponentially. So this model is only applicable for a population having a limited number of population. But when the huge number of population, the model is not correct. Then the next one is a single species model. Right. So this is the next model by developed in 18th century in 1835 year. So after developing the Malthusian model 1789, so a model which is called a Verhulst model, this is also called a logistic model. What this model indicates, what this model tells, what is the factor incorporating this model, right? So if we are not observing this one, up to this one, dn over dt is equal to r times n. This represents a Malthus model or Malthusian model. So if you are observing this dn over dt, r n times 1 minus n over k, this is nothing but a quadratic function, a quadratic polynomial, a polynomial which is of order 2. Then what this term indicates? So if we are taking this as Rn minus Rn square over k, what is this n square represents? That is the most important. So this n square, a single species population, so this is the intraspecific interaction between this population. That means the interaction in between the species only. Here we are having one species, a single species, and the interaction between the intraspecific reaction, the intraspecific communication between these two species only. Then what are those intraspecific? So there is a fight between these two species. In species itself, there is a fight between the food. There is a fight between the space. There is a fight between the habitat. So therefore, a species must interact with the same species. Then there are so many factors are going to involve. Now, the most important point here is, suppose if we are having a space, and in this space we are going to accommodate maximum number of people, and if we are having to accommodate the space required more than this space required people, if we are going to accommodate in this, then finally that again comes to this only. If we are going to accommodate number of people more than what the space available, then finally after some more time, so there is a big problem, and finally comes to this one only. So here, this is called the most important word and most important factor he introduced. Verhulst said it is called carrying capacity. So what is the carrying capacity? The carrying capacity means the maximum number of population sustained in that particular place or particular accommodation or particular habitat. So if you are observing, if we are incorporating this one, then the exponential whatever Malthus model discussed, then he can try to that exponential growth, it comes down to a particular value. That is the carrying capacity. This is the sustainable. So the maximum number of population that we can accommodate in a particular place. So Rn over 1 minus n by k. If you are observing n by k, so if n is less than k, then what is going to happen? That means n by k, which is less than 1, then dn over dt is equal to Rn. So less than 1 means the growth rate is positive. The growth rate is positive. If you are observing this one, the growth rate is positive, and if n by k, which is greater than 1, then this is the growth rate is negative. We will see what happens when the growth rate is negative. We will see in the next model. So when the population growth is Malthus model, according to Malthus model, the population is growing exponentially, but it is not correct. Then by incorporating this carrying capacity, then the Verhulst model becomes Rn times 1 minus n by k. So this is the logistic curve. So if you are observing, and again this is some nonlinear differential equation, and it comes under Bernoulli's equation, dn by dt. So we can easily solve this equation, Rn minus Rn square by k. This is comes under some Bernoulli's equation. Even though it is a nonlinear equation, we can easily solve the Bernoulli equation. That is the only nonlinear equation we can solve easily, because every nonlinear equation it is not solving easily by using our regular methods we are using in differential equations, right? So we can easily solve this logistic equation. So the solution for this one, n of t is equal to k over 1 plus n over k over n naught minus 1 e power minus rt. So if you are observing here, r is an intrinsic growth rate, so e power minus rt. So if you are observing, if r goes to infinity, the intrinsic growth rate, if r goes to infinity, then it becomes e power minus infinity. Then it becomes 0. It becomes 0. Then it becomes k by plus 1. So that means when we are using, when suppose when k is equal to n naught, when n naught is equal to some k, the initial population is equal to the carrying capacity, then this term is goes to 0. Then it is equal to the population is nothing but the carrying capacity. So if it is having more than population, so after carrying capacity, if the population is more, then what is going to happen? If we are going to incorporate what we are required, so if we are putting more population, even more than carrying capacity, after some time, then it goes down slowly and comes to the carrying capacity. So when the carrying capacity, which is this is 0, which is some initial condition, when k which is less than n naught, then it is growing, and it comes to the population, the carrying capacity. So we are restricting, we are restricting, and we are putting some factors in the Malthusian model. Then our exponential model comes into a logistic model, and this is a very important model in a single species population. Right. Next, in a single species population, sir.
I have a doubt now. As you're saying that exponential is some logic model, then when we consider the that in that we concluded with exponential function, then why can't we say that it is a logistic model?
Sir, sorry, I didn't get. Please.
Sir, we go for previous.
Yeah.
Finally, you said that finally, when we have an exponential function, so that will be a logistic model, say.
Okay.
So in the previous example, in the growth problem, in growth problem also we will be considering the exponential function itself.
Yeah.
Then why we not mentioning that as logistic model?
This is an exponential growth model. This is not.
Can't we say that it is an logistic model when it is an exponential growth model?
Yes.
So
exactly.
can't we say that? So, up to my knowledge, I think when we consider a linear equation, linear differential equation, or non-linear differential equation, both will be considered as that can be solved by using logistic model.
Yeah, we can solve that nonlinear differential equation in a logistic model. We can easily solve that nonlinear differential equation. So if you are observing the right hand side term, it is a quadratic term.
Yes, sir. For that reason only we are making that as logistic model. I came to know
Exactly.
that. So if we consider a linear differential equation,
sir.
If we consider linear differential equation, can we
Okay.
make that as a logistic model? Can we come across with logistic model?
No.
Is it not
No.
possible, sir?
Not possible, because if we are observing the solution of this equation, we are always getting this solution. We are always getting the solution is always in an exponential solution.
Yes, sir.
So where that term?
Yeah, that's why I got
Yes,
a doubt.
yes, sir. Yes,
Solve
sir.
differential equation. Can't we
Exactly.
model that as logistic model? So is there a logistic model is preferably for second degree means non-linear differential equation?
Exactly, sir. Exactly. So this is the term Rn minus Rn square over k. This is the nonlinear term.
Yes, exactly, sir.
So from this we are going to, this is the logistic curve, and this is the one side is concave up, and next one is the concave down. Concave up is there and the concave down is there. And if you are observing, this is some a point which is also called a stable point, or which from that point we can change the curve from this shape to this shape.
Okay, sir. I got it, sir. Thank you so much, sir.
Right. So this is a logistic model, because why we are going to incorporate this term is very important. We are cut down that exponential growth. This is not at all possible in ecological model, and by incorporating, because there are so many factors are not considered in Malthusian model. So therefore, by incorporating this term, we are restricting that exponential growth into some carrying capacity. Right. So the next one is, if you are observing this one, this is the most another important factor he is introducing. His name is LA. And if you are observing up to this one, Rn into 1 minus n by k up to this one, this is the logistic growth model. This is the logistic model. And if he is going to incorporate that n by k naught minus 1 term, what is this term? Because this mathematician observed in a nature, he is a biologist, and he observed in the 1920 or 19th century. He observed one factor observation in population. Because in the previous, if you are observing in the logistic model, then if n by k which is greater than 1, then what is going to happen? The growth rate is negative side. If n by k which is greater than 1, then the rate of change in the population, that means the growth rate, which is negative. Is this possible? Then this Alec effect, then what he says, when his observation, the Ali effect observation, suppose if we are taking some population, immediately this population cannot produce the next growth, because there are some mating period is there are because up to certain age there are some adults, and they can grow something. After that one, they can accommodate, and they can the mating stage happens in the population, because population having that having no age, if that population density, then it cannot grow up to some population, because when we are observing this one, this is the growth rate dn over dt up to some k naught. If you are observing this population, the rate of growth of the population is negative. What it indicates? This indicates up to certain extent of the population, because they are very little born child, and they are not having certain age to meeting somebody people, and they are not in a position to develop their growth. So up to certain period, the growth rate is not possible. After this k naught, then the growth rate is coming, and then it comes to the carrying capacity. It comes under Verhulst model. So in Verhulst model, he didn't explain when the growth rate is negative. When n by k is less than 1, greater than 1, the growth rate is negative, but he didn't explain. Then the next, the Allais effect, then this is very important in the ecological models. Then he introduced the term n by k naught, this k naught, which is called the threshold point. Up to the threshold point, then there is no growth rate. The growth rate is always negative. After this threshold, then the growth rate is growing, and finally end up with this carrying capacity. So after that k naught, so if you are observing this figure, after this k naught, then the rate of the growth of the population grows and ends up with this carrying capacity. So this is very, very important model. So the total number of individuals in the population, K is the carrying capacity, K naught is the Allais effect threshold, or is the intrinsic growth rate. This is the gradual development of the model, single species models. And then the next one. So if you are observing, so this is the single species population. And the next one, if two species are interacting with each other, suppose generally we are having some prey and predator models are there in our literature. So some predator is there, some prey is there. These are the standard models. These models are created by the mathematicians Lotka and Volterra. So this is the growth of the population, and this is the growth of prey is the P is the density of the prey population, and this is the prey predator population. This is a two-dimensional system. When we are having two population, one is a prey population and another one is a predator population. Always predator attacks to the prey. Whenever the prey attacks, if you are observing, this is A1P minus B1ZP. If you are observing, this is minus A2Z plus B2PZ. So if you are observing dP by dt is equal to A1P, up to this is a Malthusian model, and up to this dz over dt, which is equal to minus A to Z, up to this is also a Malthusian model, but it is the decay model, because this is the negative minus A to Z. This is the decay model. So up to this one, the models are Malthus model. And if we are observing this term, this is the term we call it as interaction. Interaction between the species. So when the predator interacts with the prey species and the predator interacts with the prey species, and this one, the most important, this term B1, that is the growth rate of that species of this predator when the predator, the prey interacts with the predator. The most important, this is minus B1. B1Z That means Z, this is the predator, interacts with the prey. So that means we can call it as this prey is going to encounter this predator, the predator Z, if we are writing like this, B1 PZ. If we are a predator, if we are encounter that predator with this prey, so this function is called a functional response. That is very, very important. So this is the predator functional response. That means predator is going to attack the prey in a which response. So from this we can develop so many models. If we are observing this term minus B1P, this is a linear model. That means a linear response. So whatever the density of the predator, this is the prey and this is the predator. Then whatever the prey is available, the predator is attacking. Whatever the prey is available, the predator is attacking. Whatever the prey is available, the predator is attacking. This is the linear functional response. So in this model, why this negative term? When the predator is attacking prey, then the predator gains some food. Whenever it gains some food, then the predator is going to develop their population. Then this B2, then this plus B2, then it develops their population. When this predator attacks this prey, then the population of the prey is decreasing. In the decreasing in the linear functional response. So we are having the analyzing of this model, that is the different story. We are how they are creating the models, right? Now when we are observing in our general life, in our general observation, suppose when predator is there, it is attacking prey. Always predator is attacking prey in a linear fashion. This is not at all correct. Why? Because when the predator is attacking some prey, after some time, the predator is, because of getting more food, the predator is going to take some rest. Because that food is more. So therefore, there is some time period, some time gap is there to encounter the next food, the next prey. It is not going to happen always linearly. That is observed by the famous mathematician who is called Holing. So C. Holing is a mathematician. He observed that the predator is attacking the prey. This is always not in a linear fashion. Then he is going to observe the response of the prey in a different, this is the predators, how the specialist predator is there, generalist predator is there, and how they are response. See here, functional response is the number of prey successfully attacked per predator as a function of prey density. It describes the way predator responds to the changing density of the prey. The predator can change the density of the population of the prey because it is always attacking the prey. It is observed by Holing, considered 3 types of functional responses. The first type of functional response, there is a linear relation between prey density and the maximum number of prey killed, while in type 2, proportion of prey consumed declines monotonically with prey density. Type 3 is described by sigmoid relation, which proportion of the prey consumed is positively density dependent. So if you are observing this one, so this is the type of response. It is a linear response. This is another type of response. This is another type of response. This is another type of response. All these responses we can accommodate in a mathematical notation. So if you are taking alpha p, then it is a linear response. A polling type 2 response, this is a response alpha p by p plus a. This is another type of response. This is another type of response. There are so many types of responses available in the literature. So we can accommodate that response of the predator with the prey. Then we can analyze the model and we can apply the response to the model, and we can what the dynamically changes in the population growth rates of prey predator. So this is a two-dimensional models, and this is some mathematical analysis, and we can incorporate some covers and a three species models are we are described here by depending upon more functional responses. And because the time is also almost 6:30, sir, thank you very much, sir.
Thank you, sir, for your lecture. Is it audible? Okay.
Yes, sir.
Thank you. Thank you, sir. To ecology and epidemiology. This is the time for question and answer session. If you have any doubts, please post in the Q&A box, sir, so that sir will clarify your doubts. Thank you, one and all, for your good support and good response and valuable support. Today's session concludes with vote of thanks by our co-convener, Dr. T. Srinivasrao garu.
Good evening to all. On behalf of the Department of Mathematics and participants, I would like to express my heartfelt thanks to our today's resource persons, Dr. N. Fanikumar garu and Dr. C.V. Pawan Kumar garu, for their valuable lectures. Dr. N. Fanikumar sir gave an overall view on the basic models of various ecological interactions with a single species, two species, and three species, with their chaotic behavior. And Dr. C.V. Pawan Kumar sir has covered fundamentals of linear algebra, in which geometrical importance of linear combination of vectors, orthogonality, projections, Gram-Smith process, and linear regression. Today's session is really enjoyable and enlightening us with the mathematical modeling and applications of linear algebra for exploring the knowledge in teaching community. This session has opened new ideas in faculty members, strengthening their research abilities. So, thank you, dear participants. Today's session is over. Feedback link shared in WhatsApp group, YouTube live links, and QA box. It will be in active mode for 1 hour. Later, we will disable it. So thank you for attending this session. You can leave the session now. Thank you, one and all.
you.